Good afternoon, students. In today's class, we are going to discuss about three important modulation schemes, that is pulse amplitude modulation, pulse width modulation and pulse position modulation. In the first of this series, I am going to take up this pulse amplitude modulation, PAM. In PAM, as you can see in figure 1, this is the original signal and this is the PAM signal. Okay. In this PAM scheme, that is pulse amplitude modulation scheme, samples of the original signal are taken at regular intervals of time. As you can see, these are the samples taken at regular intervals of time for this original signal. Each sample is a pulse whose amplitude is determined by the amplitude of the original signal at the instant of time at which samples are taken. Okay. So each sample is nothing but a pulse and its amplitude is determined by the amplitude of the original signal, okay, at which time of instant of time the sample is taken. Okay, suppose sample is taken at this instant of time, the amplitude of this pulse is determined by the amplitude of the original signal at this instant of time. If a sample is taken at this instant of time, then its amplitude is determined by the amplitude of the original signal at this instant of time. That means the amplitude of the pulses of the samples taken is determined by the amplitude of the original signal at the instant of time at which samples are taken. Now, how many samples are to be taken like this? That is the question. Okay. If enough samples are taken, then a reasonable approximation of the signal can be reconstructed at the receiving end. If you take less number of samples, then it may not be possible to reconstruct this original signal at the receiving end. If you take more and more samples, that is enough number of samples, then it is possible to reasonably approximate the original signal at the receiver end and reconstruct it. Okay. The next one is, this is the principle behind PAM. Okay. Now, how this PAM can be generated, that we will see next. Generation of PAM. For this simple scheme can be used. Okay. Now, it is very easy to generate and demodulate PAM signal. The signal to be converted to PAM is fed through a switch which is controlled by a pulse train. Okay. So, as you can see, this is the original signal which is fed to a switch. This is the switch. Although here ordinary switch is shown, this switch is controlled by a pulse train. That means when a pulse is present, that is the signal is at high level, switch is closed. When the pulse is absent, the signal is at low level, switch is open. This way the switch can be closed or opened based on the presence or absence of the pulse here. Okay, it is pulse operated switch, we can say. So with this control action of the switch, with the help of the pulses, we can get pulse amplitude modulated waveform at the output terminal of the switch. So here at the output terminal of the switch, we get pulse amplitude modulated waveform. Next, this pulse amplitude modulated waveform is fed to a pulse shaping network. Okay. So this pulse shaping network gives these pulses the flat tops, as you can see here. Okay. Here the tops are not flat. These tops follow the pattern of the original signal, whereas here after pulse shaping network we get flat tops for the PAM signal pulses. That is the purpose of using this pulse shaping network. Now, how to demodulate this PAM? For this, we can use this simple setup. Okay. So, in the receiver, at the receiver side, the pulses are detected by a standard FM demodulator. Okay. So, this is because these output pulses after this pulse shaping network can be again used to frequency modulate the carrier to form something known as Pwm Ppm system, that is Pwm Ppm system. Such Pwm Ppm signal is applied as input to this demodulator, where it is applied to the frequency demodulator first. Okay. Then they are passed to an ordinary diode detector, okay, where amplitude demodulation takes place, and it is followed by a low pass filter as shown in this figure 3. So, what should be the cutoff frequency of this low pass filter? Okay, that is the question. So, if this cutoff frequency of this filter is greater than the highest signal frequency component of the original signal, but at the same time much less than the sampling frequency of the pulses, then the original signal can be recovered at the receiving end without distortion. This is very, very important here. Okay, I will repeat it once again. If the cutoff frequency of the filter is greater than the highest signal frequency, but at the same time much less than the sampling frequency of the pulses, then the original signal can be recovered at the receiving end without distortion. So this is the concept behind demodulation of the PAM signals. Okay, now if we come to the frequency spectrum of PAM, okay, so the first in figure 4, the first part, that is A part, shows the frequency spectrum of the original signal which we have considered here. Okay, so it is having a highest frequency component, that is FM, from 0 to FM. This is the frequency component contained in the original signal. Then what about the frequency components contained in PAM signal? If we are curious to know about that, then this frequency spectrum of the Pam signal contains the modulating baseband signal. Okay, that is, this same thing is shown here also. That means it contains the frequency spectrum for the baseband modulating signal as well as some additional components. Okay, these additional components are like a pair of sidebands around each harmonic frequency of the pulse sampling frequency. Okay, so for every pulse, okay, for every pulse with a sampling particular sampling frequency, we will have pair of sidebands. Okay, so that's why the frequency spectrum of Pm looks like that. Okay, as you can see here, this Fs is the sampling frequency, and that's why we have one sideband, lower sideband, which is having Fs minus Fm, and upper sideband having Fs plus Fm. Next, sampling frequency is 2Fs, where the lower sideband is having this component 2Fs minus 2Fm, and upper sideband is having the component frequency component of 2Fs plus 2Fm. So this is the frequency spectrum of this Pam. Now the merits and demerits of Pam. Okay. Generation and demodulation of Pam is very simple. This is the advantage that we have in Pam. But Pam produces amplitude variations, as you can see. Okay, whether it is this kind of signal or this kind of signal, as you can see, it produces amplitude variations. And as you all know, noise always affects the amplitude of the modulated waveform or waveform which is transmitted. Okay, so that's why here also noise affects the Pam waveform. Okay, and since its pulses of the Pam signal are having varying amplitude, as you can see, the amplitude is not constant. Amplitude is as per the amplitude of the original signal or modulating signal. Since it is having pulses of varying amplitude, power required to transmit them is also not constant. So it keeps on varying. This is another disadvantage of Pam. Next, we will move on to pulse width modulation or PWM. Let me explain this PWM with the help of this input-output waveforms first. So this pulse width modulation PWM is a scheme of modulation wherein the pulse width, that is width of the pulses, will vary according to the instantaneous amplitude of the modulating signal. That means if the instantaneous amplitude of the modulating signal is high at a particular instant of time, then the width of the pulse will be high. If at any instant of time the amplitude of the modulating signal is less, then if the sample is taken at that point of time, the width of the pulse will be less. So this way what varies here is width of the pulses. But how exactly the width of the pulses can be varied? For this there are three variations of PWM which are possible. The first one is leading edge of the pulse is held constant and change in the pulse width with the input signal is measured with respect to the leading edge. That is scheme A. Okay, basically what happens here is leading edge, this is the leading edge of the pulse. Okay, here also for the output PWM waveform, leading edge of the pulse is held constant along with this leading edge, and width of the pulse varies according to the amplitude of the signal. Here amplitude is more, that's why width is more, as you can see. Okay, here amplitude of the modulating signal is less, in fact it is negative. Okay, that's why width of the pulse is also less, but the leading edge of the pulse coincides with the leading edge of the pulse train. Okay, leading edge of the PWM pulses is held constant here. Okay, and change in the pulse width happens as per the input modulating signal, and it is measured always with respect to the leading edge. Okay, width of the pulse is measured with respect to this leading edge. Width of the pulse is measured with respect to this leading edge. This is scheme A. Whereas in scheme B, tail edge is held constant and pulse width is measured with respect to it. Okay, that means tail edge. This is the trailing edge or the tail edge of the pulse trains, as you can see. Okay, so here this is held constant; it won't change. Okay, whatever change in the width has to happen will happen as per this trailing edge. Okay, so the width is now same as this, whereas it is with respect to the trailing edge. Here the width of this pulse is same as this, whereas it is with respect to the trailing edge that the width is measured. Okay, so this is scheme B. Whereas in scheme C, as you can very well imagine what may happen, the center of the pulse is held constant. Okay, so this is the center of the pulse, mid of the pulse. This is held constant. If at all any change in the width has to happen, it will happen with respect to the center of the pulse. Okay, here also the same thing. So this is the center of the pulse, which coincides with this. So width is measured with respect to center of the pulse. Width may be more, width may be less, but it is always with respect to the center of the pulse. So that's why this is scheme C. Okay, this way we can have different variations of PWM which are quite possible. Now next, having understood the concept behind this pulse width modulation, we will move on to the modulation of PWM signal, generation of PWM signal, how exactly it can be generated with the help of a circuit. So this circuit, simple circuit based on IC 555, that is timer IC, we can generate PWM signal. Okay. So basically this IC 555 is configured as a monostable multivibrator here. Okay. So here modulating input signal is applied at the control voltage input, that is pin number 5 of this 555. Modulating signal is applied as the input. Internally, the control voltage is adjusted to the 2/3 of VCC internally, internal to this IC. Externally, applied modulating signal changes the control voltage and hence the threshold voltage level. As a result, the time period required to charge the capacitor up to the threshold voltage level changes, giving PWM signal at the output as shown in figure 2. Okay. So this is the capacitor and this is the resistor. Okay. So here internally the control voltage is adjusted to 2/3 of VCC. Externally, whatever modulating signal we apply at pin number 5, this controls the threshold voltage level. It changes the threshold voltage level. As a result, what happens is the time period or time required to charge that capacitor C, okay, up to the threshold voltage level also changes. It won't remain constant. Hence, we get PWM voltage or PWM signal at the output, that is at pin number 3 of this IC as shown in that figure 2. Next, we will move on to PWM demodulation. This block diagram explains the PWM demodulation. Okay, here the received PWM signal is applied to Smith trigger circuit, okay, which is shown in the first block of this block diagram. Okay, this Smith trigger removes the noise in the PWM incoming PWM waveform. Okay, then it is applied to a ramp generator and then to synchronization pulse detector circuit. Okay. So what is the use of ramp generator here? Okay. So this ramp generator produces ramps for the duration of the pulses such that the height of the ramps are always proportional to the width of the pulse width modulated waveform pulses. Okay. Incoming pulse width modulation signal has got pulses of varying widths like this. Okay. With more pulse width like this or less pulse width like this. So this ramp generator will generate ramp. Okay, ramp signal is something like this. Okay, so here the height of this ramp depends on the width of the pulses. If the width is more, then the height will be more. If the width is less, height will be less, and so on. Okay, this way this ramp generator will generate ramp signal whose amplitude will be proportional to the, or height of the ramp will be proportional to the width of the incoming PWM pulses. Okay, and the maximum ramp voltage retained will be retained till the next pulse. Okay, whatever maximum ramp voltage is achieved, that will be retained till the next pulse. Okay, then synchronization pulse detector produces reference pulses with constant amplitude and pulse width. Okay, the job of the synchronization pulse detector is to produce reference pulses where these pulses will be of constant amplitude and constant width. Okay, that means a continuous pulse train like this, something like this. Okay, so these pulses are delayed by specific amount of time. These pulses are delayed by specific amount of time. The delayed reference pulses and the output of the ramp generator are added with the help of the adder circuit, as you can see there. The next block is adder circuit. In this adder circuit, the output of the ramp generator and the output of the synchronization pulse detector, that is delayed reference pulses, are added together. The output of the adder is given to the level shifter, as you can see there. Okay, so here the negative offset shifts the waveform down, which is clipped off with the rectifier. Okay, the job of the level shifter is to shift the whole waveform after the adder, whole waveform down. Okay, because of the negative offset voltage, the whole waveform will be shifted down, and then this rectifier, as you know, rectifier, what it does, okay, it just clips off the negative portion of the waveform and produces the positive portion, that is produces kind of DC output, isn't it? Okay, so that is what this rectifier does here also. It just clips off the negative portion of the waveform. Okay, finally the output of the rectifier is passed through a low pass filter to recover the modulating signal. Okay, so this simple scheme can be used for the demodulation of PWM waveforms. So in this discussion, we have seen the concept behind pulse width modulation, that is PWM, and how exactly the PWM signal can be generated with the help of this simple circuit, and how exactly the demodulation of PWM can be done with the help of this block diagram. The next modulation scheme we are going to discuss is pulse position modulation, that is PPM. This particular modulation scheme is different from the previous two modulation schemes we have discussed, that is pulse amplitude modulation and pulse width modulation, and this one is quite interesting also. In this modulation scheme, basically the amplitude and width of the pulses are kept constant. The width of the pulses doesn't vary as per PWM scheme, or the amplitude of the pulses doesn't vary as we have seen in PAM. Both the amplitude as well as width of the pulses are kept constant, while the position of each pulse with reference to the position of a reference pulse is changed according to the instantaneous sampled value of the modulating signal. Basically what changes here is the position of the pulse. Okay, it is changed with respect to the instantaneous sampled value of the modulating signal. This is the principle behind pulse position modulation scheme. Okay, once again I will repeat, in this modulation scheme, the amplitude and width of the pulses are kept constant, while the position of each pulse is changed with respect to or according to the instantaneous sampled value of the modulating signal. Okay, that means if the instantaneous value of the modulating signal is high, okay, the position change in the position will be more. If the amplitude of the modulating signal is less, then the change in the position of the pulses will be less. This way, the change in the position indicates the value, instantaneous value of the modulating signal in this particular modulation scheme. Thus, the transmitter has to send synchronizing pulses to keep the transmitter and receiver in synchronization. Okay, this is one disadvantage of ppm, we can say. Here basically what happens is, because of this change in the positions of the pulses, transmitter has to send synchronizing pulses to keep the transmitter and receiver in synchronism. Okay, so as the amplitude and width of the pulses are constant, the transmitter handles constant output power, which is a definite advantage over pulse width modulation or PAM for that matter. Okay, because amplitude and width of the pulses are constant, constant power has to be handled by the transmitter, which is advantage. But the disadvantage is the need for transmitter and receiver synchronization, as I have already explained. Okay, this ppm can be obtained from PWM, that is pulse width modulation itself. How exactly? We will see with the help of this input output waveforms. Yes. So as I was telling you, this ppm signal can be obtained from PWM itself. In this diagram, the first graph shows baseband signal. The second graph shows periodic sequential pulses. Okay, that is inputs. and the third one shows PWM signal, where you can see the width of the pulse is changing according to the amplitude of the input baseband signal or modulating signal. Here amplitude is more, that's why width is more. Here amplitude is bit less, width is less. Here amplitude is minimum, okay, it is negative peak, so the amplitude or width of the pulse is least. Okay, this way width of the pulse is changing according to the amplitude modulating signal. That's why this represents PWM signal, that is pulse width modulated signal, and from this pulse width modulated signal we can obtain the pulse position modulated signal. Here basically what happens is each trailing edge of the PWM pulse is a starting point for the pulse in ppm. As you can see here, this is the trailing edge of the PWM signal. These are the trailing edges of the PWM signal. These trailing edges become starting edge for the ppm pulses. Okay, so this trailing edge of this PWM signal becomes starting edge for this ppm signal, and it produces a pulse of constant height and constant width. Okay, this trailing edge of this PWM signal produces another pulse of constant height and constant width, and this which will be same as the previous pulse. Okay, again this produces one more pulse as per this trailing edge. Okay, so aligned with this trailing edge. So this way it goes on producing pulses of constant pulse width and constant height. Okay, so here basically what happens is, because the position, width of these pulses is different, and because these pulses, starting position of these pulses depends on the width, automatically the position of these pulses also gets altered. As we can see, the position has between these two, it is more, it is still more here, okay, whereas it is less here. So it appears like the pulses have shifted their positions. Okay, so that's why it represents ppm signal. Okay, position of the pulse is 1:1 proportional to the width of the pulse in PWM. If the width of the pulse is more, then the position shift in the position is also more, as we can see here. Okay, if the width of the PWM signal is less, then the shift in the position of the ppm signal will also be less. That's why it is 1:1 or in 1:1 relation with the PWM signal. Okay, hence it is proportional to the instantaneous amplitude of the modulating signal also, because PWM signal is proportional to the instantaneous value of the amplitude of the baseband signal. Hence this ppm signal also becomes proportional to the instantaneous amplitude of the sampled modulating signal. Okay, and this way we can generate ppm signal from the PWM signal itself. Okay, so this is the concept behind pulse position modulation or ppm. Quite an interesting modulating scheme. Okay, so in this class we have discussed three important modulation schemes, that is pulse amplitude modulation, pulse width modulation, and pulse position modulation. Three important modulation schemes. That is the end of this session. See you in the next video session, class session. Thank you. Along with this video lectures, I request you to go through the videos which are already uploaded on YouTube by my colleagues and myself for this particular subject, and also the lecture notes which have been uploaded on WhatsApp. Okay, so please refer those things also, and prepare yourselves well for the forthcoming IIT test as well as semester exams. Thank you.